Did you know that if the single computer hosting a web page goes down, poof, it's just gone? That single point of failure, it's a real weakness in how the internet often works today. But what if there was a way for your information online to be much harder to erase? Always accessible because it sort of lives everywhere. And even, undeniably the original.
Yeah, that fragility relying on specific web addresses, that's exactly what we're tackling here. If the address disappears, well, so does the information. It's a problem.
So today we're diving deep into the Interplanetary File System, or IPFS.
Okay, interplanetary, that's quite a name. It definitely suggests something far beyond just your local network, right? Hints at a truly global system.
Precisely. And in simple terms, IPFS is a completely different way to store and find information online. Forget those web addresses, those URLs that can break or change. Instead of looking for something based on its location, like a website URL, which is HTTP, IPFS finds it based on the content itself. Think of it like naming files based on a unique, unchangeable digital fingerprint of their content.
So it's a fundamental shift, really. Less about where the data happens to be sitting right now and entirely about what that data actually is.
Right. And to really get our heads around this, we've plunged into articles from Filebase, Apollon, the official IPFS docs, a pretty lively Reddit discussion, and Pinata too. Quite the collection of sources.
Indeed. And each one sort of shines a light on a different aspect of IPFS, letting us build up a pretty well-rounded picture, I think.
Yeah, so our mission today, for you listening, is to cut through maybe some of the technical fog and really grasp the core idea, the brilliance behind IPFS. We want to uncover its surprising potential, maybe way beyond the current Web3 buzzwords, and figure out why it might just matter to you, even if, blockchains aren't your everyday thing.
Which leads us to a really crucial question. How exactly does identifying content based on what it is, how does that actually work?
Okay, yeah, it all starts with this idea called content addressing. So imagine you send a digital photo to a friend, right? And you want to be absolutely 100% sure they received the exact same photo, no changes, nobody's messed with it. Instead of asking for a file at, say, a specific website address, IPFS asks for it based on that unique content fingerprint.
Yeah, think of it like this. Instead of saying, go to the library, shelf C, book number 12, you're effectively saying, find me the exact copy of Moby Dick that contains this specific typo on page 72. It's about the content's unique properties.
Exactly. And these unique identifiers, these sort of digital typos for the online world, they're called content identifiers, or CIDs. These CIDs, they're created using something called cryptographic hashes of the data.
Right. And what's crucial here is that a cryptographic hash is, well, it's kind of like a super efficient blender for data. You put in any amount of data, could be a single word, could be a whole movie, and it spits out this short, fixed-length string of seemingly random characters. But the key, the absolute key, is that even the tiniest, smallest change to the original data results in a completely different output hash. It's like a digital tamper-proof seal.
And this immutability, this verifiability that CIDs provide, it's a real game changer, honestly.
Yeah.
If you retrieve something using a specific CID, you can be absolutely sure that the data you get is exactly what was originally shared. Because any alteration, any tiny change would have produced a completely different CID. The link would be broken, essentially.
So if you have, say, a research paper with a certain CID and someone tries to sneak in a changed paragraph, well, the CID just won't match that tampered document anymore. It's a built-in integrity check that travels with the content itself.
Now, it's probably worth clarifying that these CIDs aren't exactly the same as those regular file checksums you might see sometimes, like SHA 256. While they both use hashing, CIDs actually contain a bit more information, which makes them even more useful in the IPFS context.
Yeah, that's a good point. Those additions include details like how the data is encoded, they call it the codec, and also which specific hashing algorithm was used, which is the multi-hash part. This makes CIDs kind of self-descriptive. The system knows how to handle the data just by looking at the CID itself. Pretty neat.
And just a quick heads up on CID versions, you might see older ones. They often start with QM, and then there are newer, more flexible versions called V1. The main difference for you, really, is that V1 is designed to be more adaptable, more future-proof for different types of data and hashing methods down the line.
Right. But the core takeaway is the same. The CID acts as the permanent verifiable address for your content on IPFS, and it's determined only by the content itself, nothing else.
Okay, so we get how content gets its unique fingerprint, the CID. But where does all this uniquely identified content actually live? That brings us to the whole decentralized nature of IPFS.
Exactly. IPFS isn't relying on big central servers like, the traditional web with HTTP. Instead, it's a decentralized peer-to-peer network. Think of it more like a web, a mesh of computers where data can be stored across many different machines, or nodes as they're called.
And this decentralization, it unlocks some really compelling advantages. We saw this highlighted in the Aplon piece and that Reddit discussion. For starters, you get a significant boost in availability and resilience. Remember how we started talking about websites disappearing if one computer goes down? Well, this decentralized approach directly tackles that. It creates a much more robust system.
Yeah, imagine it like this. If one server hosting a website under HTTP goes offline, poof, the site just vanishes, right? But with IPFS, because the data can be scattered across potentially hundreds or thousands of nodes, there's no single point of failure. If one computer hiccups, or 10 computers hiccup, the data can likely still be accessed from others. So you're moving from a fragile setup to this resilient web of information. It's always accessible, ideally, because it lives everywhere.
Plus, this distributed approach can lead to safer, faster, and maybe even cheaper file sharing. Files can be retrieved from the nearest computer on the network that has a copy, which could speed up downloads and also reduce the bandwidth strain on any single server.
Exactly. So if you're in Tokyo and the closest copy of the data you want is maybe in Seoul, you might download it from there instead of pulling it all the way from a server in New York. Much more efficient.
But let's not forget that built-in verifiability, thanks again to CIDs,
Right.
because you're always requesting data based on its content hash, you can trust that what you receive is the genuine article. It doesn't matter which peer actually provides it to you.
Right.
This also makes the whole network more resistant to outages.
But that Reddit analogy comparing IPFS to BitTorrent, it's actually pretty spot on. Instead of downloading a file from just one central source, you're grabbing small pieces of it from multiple users, multiple peers, simultaneously.
Okay, so to really nail this down, let's do a quick compare and contrast. IPFS versus good old HTTP, maybe drawing on that Geeks for Geeks article. HTTP works on that centralized client-server model, right? Your computer, the client, asks a specific server for data at a specific address.
Yeah, whereas IPFS, as we've said, is decentralized. It's peer-to-peer, completely different architecture.
And the way things are found is different too.
Fundamentally different. HTTP uses location-based, addressing that URL you type in your browser. IPFS uses content-based, addressing that unique CID, the fingerprint.
And if a server hosting an HTTP website crashes, well, the site goes dark. With IPFS, because there are likely multiple copies across the network, access should hopefully continue.
And bandwidth bottlenecks can really plague HTTP when lots of people hit the same server at once. IPFS, though, has the potential for higher overall bandwidth because it can pull data from multiple sources concurrently.
Right. And finally, making your stuff public on HTTP usually means setting up or paying for a hosting server. With IPFS, any node that chooses to store your data effectively becomes a host for it.
It changes the whole hosting dynamic.
Okay, so we've covered the what and the why of IPFS being decentralized. Now let's maybe take a quick peek under the hood at the how. How does it actually work at a high level?
Yeah, the official IPFS docs, they break it down quite nicely into 3 core jobs, basically, for its underlying systems. There's representing and addressing data, that's the CIDs we talked about. Then there's routing data, figuring out where it is. And finally, transferring that data to you.
Okay, so for representing data, we have those CIDs, and then there's something called IPLD, or interplanetary linked data. Think of IPLD as how IPFS organizes and connects different pieces of content, sort of like how folders contain files on your computer, but much more powerful. It uses this clever data structure called a Merkle DAG.
Right, DAG meaning directed acyclic graph. Fancy name, but imagine it like a tree structure where the root hash effectively summarizes everything below it. And if even one tiny leaf, one tiny bit of data changes anywhere in that structure, the root hash, the main CID for the whole thing, changes completely.
Ah, okay. So that allows for really efficient verification of the entire structure, right?
Exactly. You can verify the integrity of a huge data set just by checking that one top-level CID. If it matches, nothing inside has been tampered with. Super efficient.
Okay, so that's representing data. What about finding it?
Right.
The routing part.
For that, IPFS uses something called a distributed hash table, or DHT. Think of it like a massive, globally distributed phone book, but for data. When you're looking for a specific CID, you consult this phone book, the DHT, to find out which computers, which nodes on the network are currently holding that data.
So it's like asking the network, hey, who's got the data with this fingerprint?
Pretty much. And the DHT helps you find the nodes that raise their hand and say, yep, I've got a copy. And importantly, this whole lookup process happens without relying on any single central directory or server. It's all peer-to-peer.
Got it. And then the final piece, transferring the data.
That's where Bitswap comes in. Bitswap is the protocol that IPFS nodes use to actually exchange the data blocks with each other. So if your node needs a piece of data identified by its CID, it asks its neighboring nodes, its peers, hey, do you have this block? If a peer does have it, Bitswap manages the efficient transfer of that data block back to your node. And what's kind of neat is that nodes also keep track of what data their peers seem to be looking for. So they can even proactively share relevant blocks if they happen to acquire them later. It's quite clever.
And one more piece, IPFS gateways. These seem pretty important for bridging the gap, right?
Absolutely crucial. Because most of us still use regular web browsers that speak HTTP, not IPFS natively. Gateways act as translators. You request IPFS content using its CID, but you do it through a special gateway URL. The gateway then goes and fetches the content from the IPFS network behind the scenes and serves it back to your browser in standard HTTP format.
Ah, so that's how you often see those long URLs with the CID kind of embedded in them.
Exactly. It means you can access content stored on IPFS without needing to run any special IPFS software yourself. Just use a public gateway.
Makes sense. Now, someone on that Reddit thread brought up an interesting point about IPFS maybe being a bit secretive. They're questioning how easy it is to trace the original source of a file.
Yeah, I saw that. And it's true that pinpointing the very first uploader of a file that's become really popular and is now cached on, thousands of nodes, that can be genuinely difficult.
Because once content gets popular, it just gets replicated everywhere, right?
Yeah.
So it looks like it's coming from many places at once.
Precisely. But the crucial thing to remember, and this goes back to the CIDs, is that the content itself is entirely public and its authenticity is verifiable thanks to that CID. Who uploaded it first becomes less important than knowing you have the correct untampered data.
Right. The focus shifts from the origin story to the integrity of the data itself, which is guaranteed by the crypto.
And there are tools you can use to try and discover which nodes, which peers are currently providing or hosting specific CIDs. But yeah, with widespread caching, the idea of a single original source gets a bit blurry.
Okay, this brings us to a really vital point, persistence. How long does data actually stick around on IPFS? And what's this whole business about pinning? That Reddit user asked a great question. What happens to my data if my computer crashes? Is it really out there forever on this distributed network?
Yeah, that's a super valid concern, and the answer is not automatically. Just because you add data to IPFS using your own node doesn't mean it's permanently etched into the digital ether forever and ever. Data on IPFS is only guaranteed to remain accessible if someone, somewhere, actively pins it.
Okay, so pinning. What does it actually mean in practice?
Pinning basically tells an IPFS node, either your own or usually a dedicated pinning service, hey, this specific piece of data identified by this CID is important. Keep a copy of it, store it reliably, and don't let your automatic cleanup processes delete it.
Ah, cleanup processes. So nodes don't just keep everything forever?
No, exactly. That Filebase article mentions this. It's called garbage collection. To manage their stored space, IPFS nodes might automatically delete data from their local cache if it hasn't been accessed recently, or crucially, if it's not explicitly pinned.
Okay, so if I just upload something using my own IPFS node on my laptop, I don't pin it, and then I turn my laptop off.
Then yeah, that data might eventually disappear from the network if no one else happened to request it and cache it while your node was online. It needs someone to actively preserve it.
Gotcha. And this is where pinning services come in, right? Filebase, Pinata, Reddit, they all mentioned these.
Exactly. These are services, often paid services, that you can use to ensure your data does remain available on the IPFS network, even if your own computer is offline or crashes. They essentially act as reliable custodians. They run robust IPFS nodes 204/7 and guarantee they will keep your PIN data stored and accessible.
And some services, like Filebase, even offer redundancy, storing copies in different geographic locations.
Yeah, that's a big plus for resilience. If one data center has an issue, copies still exist elsewhere.
Okay, so bottom line. The IPFS protocol provides the framework for distributed storage, but ensuring long-term persistence and availability usually requires active pinning, either doing it yourself reliably or using a pinning service.
Correct. Now, let's maybe pivot a bit. IPFS got strongly associated with NFTs and Web3 early on, but let's explore some of the other really compelling, maybe less obvious applications. Drawing from Filebase and Apple on here.
Absolutely. Because while storing NFT artwork is, a visible use case, the potential of ITFS goes way beyond that. Like, consider distributed package management systems, similar to NPM for JavaScript developers.
Right. Instead of software packages living on centralized servers like GitHub or NPM's registry, they could be distributed and accessed via IPFS using their CIDs,
And any update to a package would generate a new, distinct CID.
which gives you a transparent and automatically verifiable history of changes. Developers could be certain they're using the exact version they intend to use. That's pretty powerful.
Yeah. Another fascinating area mentioned is hosting software containers, like Docker containers.
hmm Imagine being able to pull a container image using its IPFS CID instead of only relying on a central registry like Docker Hub.
Okay, what's the benefit there?
Well, Apollon points out it could simplify things a lot. You potentially bypass the complexities of managing domain names, DNS, user permissions for your container registry. It makes deployment potentially simpler and applications more portable.
Interesting. Filebase also brought up decentralized e-commerce websites, platforms like e-commerce.
Yeah, the idea is you could build an entire online store, product listings, images, maybe even handling crypto payments completely hosted on IPFS. No need for traditional web hosting providers.
So you just upload your website files to IPFS, get the CID, and people access it via a gateway.
Essentially, yes, it could lower the barrier for entry for small businesses or individuals wanting to sell online.
Filebase even mentioned the potential for decentralized operating systems using IPFS for storage.
Right, though that's maybe more conceptual. The idea is the core logic might live on a blockchain, but storing the entire OS, all the big files, on-chain would be incredibly expensive.
So IPFS is much better suited for the large data storage aspect.
Exactly. It highlights that efficiency difference between IPFS and many blockchains for handling large files.
Okay, here's one application that really caught my eye. Decentralized peer review for academic research.
Oh, yeah, that's a neat one. Picture researchers publishing their work maybe as an NFT to represent ownership or the publication event itself. But the actual research document, the PDF, is stored securely on IPFS. The CID of that paper gets linked to the NFT on the blockchain.
And then the peer reviews could also be recorded, maybe linked in a similar way.
Precisely. It could create a much more transparent, verifiable, and trustworthy system for scholarly communication. You combine the blockchain for immutable records of authorship and review with IPFS guaranteeing the integrity and accessibility of the actual research content via its CID.
And that's really compelling. And beyond these more novel ideas, there are these straightforward but still significant benefits like just using IPFS for decentralized storage and hosting for static websites.
Yeah.
Apollon emphasized this.
Yeah, that's a core advantage. The resilience and uptime you can get for a website hosted on IPFS can be much better than traditional hosting, simply because you eliminate those single points of failure. The site's files are served from potentially many nodes.
And just for everyday users or people dealing with large files frequently, IPFS offers a potentially safer, faster, maybe more cost-effective way to share them compared to methods that hammer central servers.
Definitely. So the common thread through all these different uses, whether it's NFTs or scientific papers or websites, is that they're all leveraging those fundamental strengths of IPFS: content addressing, data immutability, and that inherent network resilience.
Okay, now with all this talk of decentralization, blockchains popping up here and there, it feels crucial to clarify the relationship, maybe more importantly, the distinction between IPFS and actual blockchain technology. Pinata's article tackled this head on.
Yes, very important distinction. A common misconception is that IPFS is a blockchain. It's not. As Pinata clearly lays out, IPFS is a distributed file system. It's a protocol, a method for storing and accessing files. A blockchain is a specific type of distributed ledger, primarily for recording transactions immutably. Different tools for different jobs.
Okay. But they can work together really well, right?
Incredibly well.
Yeah.
Synergistically, you could say. Pinata explains it nicely. Blockchains are excellent at recording things immutably, transactions, timestamps, ownership records, but storing large amounts of data directly on most blockchains is generally very, very expensive.
Right, you hear about high transaction fees, gas costs. Trying to store a movie file directly on Ethereum, for instance, would be impractical, probably impossible.
Exactly. It just doesn't scale cost-effectively for large data. IPFS, on the other hand, is designed for efficient storage and retrieval of large files, large amounts of data. So the clever part is you store your bulky data, your video, your PDF, your data set on IPFS. Then you take the CID of that data, which is just a small string of characters, remember, and you record that CID on the blockchain.
Ah, okay. So the blockchain gives you the permanent, unchangeable, time-stamped record that this piece of data, represented by the CID, existed at a certain point in time.
Precisely. And IPFS ensures the integrity and the actual accessibility of the data itself that the CID points to.
So you get the best of both worlds.
Exactly. Pinata used a great example. Imagine storing a critical legal agreement, say a PDF, on IPFS. Then you embed the CID of that PDF into a transaction on a blockchain. Now, if there's ever a dispute later about the document's authenticity or when it was finalized, you have the blockchain entry with the CID as verifiable timestamped proof. And checking the CID against the document on IPFS proves it hasn't been tampered with since.
That's a really powerful combination. Blockchain for the immutable record keeping, IPFS for the efficient, verifiable data storage.
You got it.
Okay, so for our listeners who might be feeling a bit adventurous now, maybe wanting to explore IPFS firsthand, what are some practical ways they could actually get started?
Yeah, good question. The IPFS docs and platforms like Apollon point to several ways in. Probably the simplest way is just to use one of the public IPFS gateways right in your web browser. If someone gives you an IPFS CID for some content, you can usually just append it to a known gateway URL like ipfs.io IPFS, your site here, and your browser will display it, assuming the gateway can find it.
Okay, so no software needed for just viewing content that way.
All right. If you want to get more involved, you could install IPFS Desktop. That's a user-friendly application, bundles an IPFS node with a nice graphical interface, lets you easily add files to IPFS, manage your node, pin things, interact with the network more directly.
And then there are the pinning services we talked about.
Yep. Using a pinning service is a really convenient way to participate and make sure your own data stays persistent without you having to worry about running your own node 21047, keeping it online, managing storage, etc.
Right. And for developers.
Oh, for the more technically inclined, there are tons of tools and software libraries available in different programming languages, Go, JavaScript, Python, you name it. So you can build IPFS support directly into your own applications. And platforms like Apollon, as mentioned, are specifically trying to make it easier for developers to integrate decentralized storage and hosting into their projects without needing to become deep IPFS experts themselves. They offer simpler APIs and infrastructure management.
So basically, options exist, whether you just want to look at stuff, share some files reliably, or build the next big decentralized application.
Pretty much, yeah. There's an entry point for various levels of technical interest.
Okay, final practical question, and it's probably on a lot of minds. Is storing data on IPFS actually free? Filebase tackled this one directly.
Yeah, it's a common question.
Yeah.
And the key distinction, again, is between the protocol and the service, the underlying IPFS protocol itself. Yes, it's open source, free to use, anyone can run a node, but ensuring reliable, persistent storage, that pinning we keep coming back to, that typically involves real-world costs.
Costs like what?
Well, bandwidth, mainly. Serving data to others uses bandwidth, and then there's the cost of the hardware, electricity, maintenance needed to keep an IPFS node running reliably 24/7 with good uptime. Pinning services cover these costs and charge for the guarantee.
Okay. So while I might be able to temporarily upload data to IPFS for free using my own node, if I need that data to be consistently and reliably available for others, especially over the long term, I'm probably going to need to use a paid pinning service.
That's generally the case, yes. It's
don't-
kind of analogous to the traditional web, isn't it? The HTTP protocol is free, the TCP/IP protocols are free, but running a reliable web server with guaranteed uptime and enough bandwidth definitely isn't free. Same principle applies here.
Makes sense. Okay, so to sort of bring our deep dive to a close here, IPFS really does present a fundamentally different way of thinking about online data. It shifts the focus from where data is located to what the data actually is.
And this content-centric approach, it leads to some really significant potential advantages. We've talked about enhanced resistance to censorship, network outages, there's the inherent verifiability of information through CIDs, and it just opens up possibilities for entirely new ways of sharing and accessing digital content.
Yeah, it's genuinely eye-opening when you start thinking about the potential applications beyond just, the initial Web3 hype. Things like revolutionizing software distribution, maybe fixing academic publishing.
Yeah.
It's quite broad.
Definitely. Which leaves us with maybe a final thought for you, our listener, to ponder on. Imagine a future where more of the core internet infrastructure starts to lean into this model of content-based addressing. How might that fundamentally reshape your daily experience of using the web? from just finding information to ensuring the long-term preservation of our digital culture. What entirely new kinds of applications and services, things we haven't even thought of yet, might emerge in that kind of landscape?
Yeah, definitely some profound questions to chew on there. If your curiosity has been sparked by all this and you're keen to dig deeper, we definitely recommend checking out the official IPFS documentation that's at ipfs.io. Maybe look into some of the pinning service providers we touched on, see what they offer. Explore platforms like Apollon if you're interested in the developer side. There's a whole new realm of decentralized possibilities out there waiting.